Hey everyone, it's Mr. Thrasher once again. We are deep into our online learning. We're going to quickly look at a big idea when it comes to light and how we see. And people have asked this question. One, you may have asked it since you were in grade school. It's a common question, and there's often common incorrect answers that are given. We're talking about why the sky is blue and why sunsets are red and orange. This does have a little bit to do also with the topic of sending and receiving information, and that's really what we're getting into later on this week. But let's try and answer this question. And again, it has to do with properties of light. I have a couple warm-up questions for you. Okay, the first question is, what color is the sun? If I asked you that question, what color is the sun? What would you write down? What would be two sentences? To be honest, that ends up being kind of a complicated question, as we'll get into in a second. I have a second question for you. Again, if you were going to answer in a couple sentences, what part of the light spectrum, remember, radio waves to gamma waves, does the sun produce the most of? What would be your best guess, and maybe why? Why would you guess that? Okay, give me two sentences. What do you think type of light it produces the most of and why? And maybe your why is like, oh, I heard it on here, or somebody told me. Yeah, I'll take that. Okay, but what part of the light spectrum, what type of light does the sun produce the most of? All right, let's get into this first question. What color is the sun? Again, it's kind of tricky, to be honest. It really depends on how we're defining color and or how we're looking at the sun, what quality of the sun we're dealing with. First, the big misconception. Okay, what's the common wrong answer? Why is the sky blue? It's a reflection off the ocean. Well, that doesn't really make a whole lot of sense if you live in Kansas. All right, and you're a good 1,000 miles from the ocean. Do they see like a brown or a green sky because they are surrounded by fields and dirt and stuff? No, everywhere around the planet you see a blue sky, regardless of whether you're near the ocean or not. The sky is not blue because it's the reflection off the ocean. The ocean is not blue because it's a reflection off the sky. Both of those things are wrong. We're going to get into why in just a moment. Now, also, what color the sun is, it really depends on what you mean, because the sun would look different here on ground level versus if we were in outer space. Now, of course, we can't look at the sun, you burn out your retinas. Okay, but even if we could like dim it at least, the color you would see would be pretty different. And hopefully you'll understand a bit why by the end of this video. Okay, now we know the sun emits all the colors of the rainbow, right? Red, orange, yellow, green, blue, violet. So if you said that the sun emits all the colors, you're not wrong. If you said the sun is the color white, arguably you're not wrong either. Okay? Now, if you were going outside and you kind of glanced at the sun, if you said the sun is yellowish, okay, that seems very reasonable also. Or, I have here a graph, and this is also getting into the second question. This is a graph showing the intensity, how much light, versus the wavelength. So we have the visible light here. Okay, we have smaller wavelengths over here, bigger wavelengths over here. And this is a graph showing the proportional amounts of light for the different types of light that the sun is emitting. So this graph, this hump right here, is the curve showing the types of light that is emitted by our sun. What type of light is emitted the most? Oh, it's visible light. So for question 2, if you said visible light, nice. And to be honest, if we think about it a little bit, that should probably make sense. Because from an evolutionary standpoint, a biology standpoint, well, what color or what type of light are our eyes sensitive to? Oh, visible light. Would it be much of an evolutionary advantage, a biological advantage, for a species to develop eyes that were really sensitive to, say, like X-rays way over here? Well, no. I mean, it'd be awesome if you could see X-rays, right? That'd be so cool. But the sun doesn't really emit X-rays, and certainly almost no X-rays from the sun get to the surface of the Earth. In fact, I'll say no X-rays from the sun get to the surface of the Earth. So even if as a species you developed X-ray sensitive eyes, you wouldn't see anything because the sun isn't actually emitting X-rays. Certainly none are getting here to the Earth. the types of light that are leaving the sun, leaving the surface, and mostly getting to our surface, it's visible light, infrared light, and also ultraviolet light. So, if you said the color of the sun is visible light or white light, you're also not wrong. What color does the sun emit more than any other color? Well, it peaks right around green. So also maybe the silliest answer is you could argue the sun is green in color because the sun emits more green frequency light than any other frequency light. So is the sun yellow? Is it white? Is it green? Is it all the colors? To be honest, all of those are right. Let's figure out why a little bit longer or a little bit more as we dive in. We got to learn another topic when it comes to light, another way that light can interact, and it's known as scattering. And scattering sounds much like the word implies outside of a science context. When you scatter, things are moving in random directions. That's what's going on. So we know that light can be reflected, it can be absorbed, but it can also be kind of deflected. It can be scattered off of particles, off of atoms and molecules, okay? And there's many different types of scattering. We're going to focus on one called Rayleigh or Rayleigh scattering, but there's types known as Compton scattering and Mie scattering. Scattering actually gets kind of complicated, so we're just looking at a pretty shallow idea. We're going to focus on one type and the type that dictates why the sky is blue. What Rayleigh scattering says, here's an equation, a simplified or at least a proportion equation. It says the intensity, how much light is scattered, it is inversely proportional to the wavelength. And what that means in English is the smaller the wavelength, the more likely it is to scatter. And look at this, it's even to the fourth power. And what that means is like, oh my gosh, smaller wavelength light is way more likely to scatter than bigger wavelength light. This is saying that the wavelength has a huge part of what colors or what type of light is going to scatter right here. Based on this equation, higher frequency light is more easily scattered than lower frequency light. So let's go back and look at our types of light. We have red through violet, Roy G. Bv. Okay, what types of light have the lowest wavelength or the highest frequency? Well, these types, blue and violet with the highest frequencies are the most likely to scatter. Red light with pretty big wavelength, pretty much goes constant. It's very difficult to get red light to scatter. It pretty much moves in a straight line. But oh my gosh, green light and blue light and violet light, it scatters all the time. Think of like a really hyperactive, right? Because this is also energy, a really hyperactive, high energy child. Well, the more energy you have, the more likely you are to bounce around. So higher energy, higher frequency, smaller wavelength, the more likely it is to scatter. Whereas Peter here, red, okay, red, low energy, maybe think of lazy as an analogy, not likely to scatter, it's constant. So how can we see this? First, I'll give you an example with a laser pointer. If you've ever seen a red laser pointer, okay, they're neat, but they're kind of boring. What a laser pointer does is it shines light in one direction. And if you've ever seen a red laser pointer, I'd be doing this demo in my class, but oh well. A red laser pointer, you don't see the beam, unless like you spread chalk or something, or like you show your breath, you're like, on it. You can't see the beam, you just see the dot. Because red light goes in a straight line. Remember, to see light, it has to go into your eyes. And if all the red light is just going like this, none of it goes into your eyes until it reflects off the wall. If you want a really cool laser pointer, you get one that's green or blue. These have higher energies, and that means it scatters a lot more. You see green light because it scatters, bounces off, and goes into your eye. That's why you can see a green laser pointer, because here is an example. Here's a photon of green light, bam, scatter, and it goes into your eyes. But red light doesn't scatter. It keeps going, keeps going. So this person doesn't see any of the beam until they see the dot reflecting off the wall. Okay, let's talk about how this applies to the sun. So we know the sun emits all the colors of the rainbow. The light is traveling through outer space, no particles. Then it gets to the Earth. And the Earth obviously has an atmosphere. It has air. This line is kind of representing the beginning of Earth's atmosphere. The Earth's atmosphere is made up of particles, and particles scatter light. What type of light scatters the most? Blue light. Whereas if you look up towards the sun, the red light goes straight down, the orange light pretty much goes straight down, the yellow light pretty much goes straight down. The blue and the violet light instantly starts bouncing around. Bang, boom, pow, 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 pow. So if you're looking not toward the sun, but if you're looking away from the sun, what you're looking towards is where all that blue light is scattering. And eventually, 30 minutes later, not really, but pretend, eventually after all this scattering, a blue light might boom, hit you in the eye and you see blue. So why is the sun yellow and why is that a valid answer? Well, because look, if you're looking toward the sun, the light that makes it to your eye is red, orange, yellow. The light that doesn't reach your eyes are the blues and the violets. So the sky appears blue because the higher frequency blue light is scattered in our atmosphere. And this blue light is bouncing around before reaching our eyes. Now, hold on a second. I unfortunately meant to animate this. A lot of people ask, wait just a minute, Thrasher. Okay, I get it. Higher frequency light scatters more. But blue light doesn't have the highest frequency. Violet light has the highest frequency. If this is the reason why the sky is blue, why isn't the sky purple? Why isn't it violet? And that's a great question. And the answer to that question is, to be honest, there's several layers to it. Kind of the worst answer you might see online is they say, like, your eyes aren't as sensitive to violet. And that's true a little bit, but that's probably the weakest of all the answers. Okay, let's look back at our diagram for the light that the sun emits. Here's green, here's blue. The sun emits a lot of blue, a lot of green. Does the sun emit a lot of violet? Oh no, look, there's a pretty significant drop-off. Violet light definitely does scatter a lot in the atmosphere, but there's way less violet light than blue light in our atmosphere. So that's one significant reason. Another significant reason is, remember, your brain combines colors. The sky doesn't look navy blue, it looks light blue. And it looks light blue because there's blue light and there's violet, and, to be honest, there's some green, a little bit of yellow that's also scattering. So you're not just getting bold navy blue, you're seeing this sky blue because it's a combination. Remember, your brain is mixing colors. So it's not going to look pure violet because the sun is producing more blue light. And if there's blue light and violet and a little bit of green, tiny bit of yellow bouncing around, your brain's going to combine those colors to get to this light sky blue that we all know. Now, why are sunsets red? It's based on the same mechanism, but there's a little bit of geometry that's involved. Even if you're a flat earther, this still applies, so don't worry. Okay, when it's noontime during the day, the sun is pretty much right above you. So the light has to go through a certain amount of atmosphere. Okay, but when the sun is on the horizon, well, notice, look at this angle. Now the light has to go through way more atmosphere. More atmosphere means more scattering. Now, it's still true that blue light, higher frequency, is the more likely to scatter. But if the blue light is more likely to scatter and the red light is the least likely, think of what colors of light are going to reach your eye. Here's sunset. Is blue and violet going to reach your eye? No way. It gets scattered immediately. But because there's so much air, there's so many particles, even by the time light finally gets to your eye, the green light is pretty much all scattered away. The yellow light has made it farther, admittedly, but is also mostly scattered away. Even probably a good amount of the orange light eventually scatters away. Scattering is really a probability game. Okay, it's what's the probability of scattering. And when there's more and more particles, there's more opportunities to scatter. Even if scattering's pretty rare for orange light, with all these particles, overall, you're going to lose a lot of it to the scattering. What light makes it to your eyes? I don't know where this 80s clip art came from, but that's going to be red light. So sunsets are red because it's really the same mechanism. Higher frequency, bluer light is scattered away. Only the longer, the redder light makes it to your eyes. Real quick, why are clouds white? Well, there's another aspect of scattering. Remember, I said it's a little complicated. Different size particles will scatter different size waves of light. And so a cloud is obviously made of water. Okay, water vapor, water droplets, big water droplets, small water droplets. The smaller the water droplets, the smaller wavelength light gets scattered. The bigger wavelength light gets scattered. And clouds are made of all different size water droplets. So the clouds, with their different size particles, they're going to scatter all the different colors of light at different places. And what happens when you see all the light coming in? You see white. So that's why clouds are white, because they have different size particles. And there's another aspect of scattering that says different size particles scatter different size waves. And therefore, if there's a lot of different size particles, you're going to scatter different size waves. If you're scattering all the different waves, that's all the colors. That's white. So what color is the sun? Well, on the surface, it's yellow. If you were in outer space, there's no scattering going on, so you would see it as white. But again, in terms of like spectrum, it's green more than any other color. So hopefully that enlightens you a little bit to why the sky is blue, sunsets are red. I know my video is a little long, but I think this is a pretty interesting topic. Sorry if you disagree. Thanks for watching.